Good day, everyone. How are you, students? I'm really hoping that you're in good state now and you're doing better and fine. For today's discussion, we will be dealing with the concept of the twins paradox in accordance for the topic that we've discussed earlier about the time dilation. For this twins paradox is somewhat related to or connected to the concept of the time dilation and along with other concepts. For today's discussion, um, these are our learning objectives. First, the learners must demonstrate an understanding of the twins paradox in accordance to time dilation. So, you students must be able to understand the concept of the twins paradox. Second, the learners must demonstrate an understanding of the variety in time experienced by two people, one in space travel and one remains on Earth. So after our lesson, you must be able to understand how the time varies of that due to the different experience of the two people. And the third, the learners must demonstrate an understanding of the resolutions for the twins paradox. Before digging deeper to the lesson for today, to our lesson for today, let us first recall the concept or the idea of the time dilation. And the very essence of this time dilation is put in this quotation. A moving clock ticks more slowly than a clock at rest. It is somewhat related to a moving object has a slower time than an object at rest. Measurements of time intervals are affected by relative motion between an observer and what is being observed. As a result, a clock that moves with respect to an observer ticks more slowly than it does without such motion, and all processes, including those of life, occur more slowly to an observer when they take place in a different inertial frame. When time changes, we call it time dilation. So to dilate is to become larger. Um, the equation for the time dilation is given below. T is equal to the t sub 0 over the square root of 1 minus v squared over c squared. So the wherein the t of 0 is the time interval on clock at rest relative to an observer, or what we call the proper time. Well, the t is the time interval on clock in motion relative to an observer. V is the speed of relative motion and the c is the speed of light. Because the quantity square root of 1 minus the squared of the speed of relative motion over the squared of the speed of light is always smaller than 1 for a moving object, the t, which is the time interval on clock in motion relative to an observer is always greater than the proper time. For example, the moving clock in a spacecraft appears to tick at a slower rate than the stationary one on the ground, as seen by an observer on the ground. And every observer finds that clocks in motion relative to him ticks more slowly than a clock at rest relative to him. So the idea of the time dilation is about the time is always related to the different inertial frames or the frames of reference, and that told us on uh, on the when time goes fast or slows down. I'm hoping that you understand already the concept of this time dilation. For this concept is related to for us to better understand the concept also of our lesson for today. So let me discuss this our lesson for today, which is the twins paradox. So the very essence also of this twins paradox is put into a quotation: a longer life, but it will not seem any longer. So how is it possible? How is it that a longer life doesn't seem any longer at all. We are now in a position to understand the famous relativistic effect known as the twins paradox. This paradox involves two identical clocks, one of which remains on Earth while the other is taken on a voyage into space at a speed and eventually is brought back. So I have here a dilemma for us to give example and guide our discussion. It says, suppose there are twins. One twin will be leaving for a space voyage at a speed of 0.80 c to a star 20 light years away, while the other twin will just be left at home. Eventually, the twin on a voyage did slows, stops, returns, um, turns around and decided to get back home. Now the question is, who do you think is older? The twin who lives on a spaceship and then comes back, or the twin that stays on Earth? So I am hoping that you will be able to answer this question along with our discussion. Let us move now to the topic for today, which is the concept of the twins paradox. So, well, it is customary to replace the clocks with a pair of twins. For example, we will be naming it Dick and Jane. A substitution that is perfectly acceptable because the process of life, such as heartbeats, respiration, and so on, constitute biological clocks of reasonable regularity. Suppose Dick and Jane is twins. Dick is 20 years old when he takes off on a space voyage at a speed of 0.80 c to a star 20 light years away. To Jane, who stays behind, the pace of Dick's life is slower than hers by a factor of the square root of 1 minus v squared over c squared, where the v squared, we have mentioned this a while ago to the concept of the time dilation, where it is the speed of relative motion and the c is the speed of light. So substituting, we have the square root of 1 minus the given speed of relative motion is 0.80 c squared over the squared of the speed of light. So this is equal to 0.60 or 60%, meaning that 60% of uh, Dick's life is slower than to Jane's life. To Jane, Dick's heart beats only 3 times for every 5 beats of her heart. Dick takes only 3 breaths for every 5 of hers. Finally, Dick returns after 50 years, have gone by according to Jane's calendar, who remains on Earth, but to Dick, the trip has taken only 30 years. Dick is therefore 50 years old, whereas Jane, the twin who stayed home, is actually 70 years old now. So, in that scenario, where is the paradox? If we consider the situation from the point of view of Dick in a spacecraft, Jane on Earth is in motion relative to him at a speed of 0.80 c. But in relative to Dick, that is actually the perspective also of Jane, that Dick is um, on motion relative to him at a speed of 0.80 c. Dick changed from one inertial frame to a different one when he started out, when he reversed direction to head home, and when he landed on the Earth. Jane, however, remained in the same inertial frame during Dick's whole voyage. So, the time dilation formula applies to Jane's observation of Dick, but not to Dick's observation of her. To look at Dick's voyage from his perspective, we must take into account that the distance L he covers is shortened to L is equal to the L sub 0, uh, the square root of 1 minus b squared over c squared. So this is actually an equation of the length contraction. So this is equal to um, Dick would have to travel at the length of 20 or the distance of 20 light years, but of substituting the square root of 1 minus 0.80 c squared over the squared of the speed of light, Dick actually travel for about only 12 light years away. Where the L sub 0 there is the length of an object in its rest frame or the proper length. The L is the length of an object in motion with respect to an observer. The V is the speed of relative motion and the C is the speed of light. To Dick, goes by at the usual rate. But his voyage to the star has taken only 15 years, and his return voyage another 15 years, for a total of 30 years. Of course, Dick's lifespan has not been extended to him because regardless of Jane's 50 years of wait, he has spent only 30 years on the round trip. So in this screen, you will be able to see an astronaut who returns from a space voyage will be younger than his or her twin who remains on Earth. Speed close to the speed of light, for example, the 0.8 cc are needed for this effect to be conspicuous. So that is a proof that any one that travels on space has a slower time than the one who remains on Earth. Now, what do you think are the resolutions for this twins paradox? So for you to better understand the concept of this twins paradox and to know the different resolutions, we have to view this video about the twins paradox. Enjoy watching!
The setup for the twins paradox is as follows. Suppose I sit on Earth while you head off on a rocket ship at a constant speed for a while, then turn around and come back. We know that moving things experience time more slowly, so I'll think that when you get back, you should be younger than me. But from your perspective, the Earth with me on it is doing the moving, receding and then returning, so you think that I should be younger than you. Who's right? We'll use the fact that time rotates to sort this all out. Okay, so from my perspective, every second that passes, I stay in the same place, while every second that passes, you get farther away, and then closer. Simple enough. From my perspective, you'll take 10 seconds to get back. And since you're moving, I'll think that time is passing more slowly for you, so I'll calculate that your journey, for you, takes 8 seconds. Now, and this is the important bit, since you're moving, what you think of as the forward direction of time will be rotated relative to my perception of time. So on your outward journey, the seconds will tick away like this, and on your return journey, the seconds will look like this. From your perspective, your journey does indeed take 8 seconds. But almost immediately, we also see the solution to the twins paradox, right here. This bit of my time is unaccounted for by you. During your entire journey, you'll think that time is passing more slowly for me than for you. And indeed it is. Here and here add up to only 6.4 seconds. But because of your change in velocity when you turn around to come home, your notion of time rotates and skips right over a large swath of my time, which amounts to precisely, you guessed it, the missing 3.6 seconds. And this is the resolution to the twins paradox. Because you changed velocity, your notion of simultaneous times rotates, so your accounting of how time passes in parts of the universe far away from you will have gaps in it. Well, in reality it wouldn't have gaps because you couldn't instantaneously change direction. You'd have to fire your rockets to start heading home, and during that acceleration, your notion of time would have very, very quickly rotated through the missing gap in my journey, allowing you to properly account for the missing time. In summary, during your outward and return journeys, 10 seconds would pass for me, and I'd calculate 8 seconds as passing for you. 8 seconds would pass for you, and you'd calculate 6.4 seconds as passing for me during your outward and return journeys, and 3.6 seconds as passing for me during your acceleration, even if it was basically instantaneous. So we both agree that when you come home, you'll be younger. And indeed, this is exactly what happens when you send an atomic clock flying around in an airplane. It records less time as having passed than a twin atomic clock that stays on the ground. P.S. The time rotations I've been talking about are actually called Lorentz transformations, and they're the way that most working physicists think about special relativity and things like time dilation, relativistic Doppler shifts, and so on. Trying to understand relativity just by using basic equations for time dilation and length contraction, like is often done in beginning physics classes, will often lead to confusing apparent contradictions, because these equations don't take into account the full changing of simultaneity of events, and so on. Hey, Henry here, thanks for watching. I'd like to thank the great
Okay, based from the video, these are the idea about the resolutions of the twins paradox. First, the Earthling did not experience any acceleration, so he remains stationary here on Earth. Therefore, he can use special relativity to determine time, and so the space voyager aged less. So the special relativity is defines as the all motion is relative. The speed of light in free space is the same for all observers. Next, the space voyager felt acceleration forces during takeoff, turnover, and landing. So she cannot use special relativity and needs the idea of the general relativity, which is the relationship between gravity and the geometrical structure and the space and time. Lastly is, the acceleration cannot be distinguished from gravity and the gravity slows down clocks. So, the space voyager's clocks lost time during the acceleration and deceleration periods, and that keeps her younger. So that is all about the resolutions of the twins paradox. Now, this is actually a real life example of the twins paradox. This is Scott and Mark Kelly. They are twins and they are also an astronaut. At birth, Mark was 6 minutes older. Now he is 6 minutes and 13 milliseconds older because Mark was taken into a space voyage. So this tiny effect has been measured with clocks, not twins. So now let us go back to the question that I mentioned before. So who is older now? The a person who takes into space voyage and then comes back, or the person who stays on Earth? I know that you really know now the answer, and I'm really sure that everyone wants also to be a space voyager for you to age less than you're on Earth. Okay, that is all about our discussion for today. I'm really hoping that you understand now the concept of the twins paradox in accordance to what the topic that is the time dilation. So thank you very much, and God bless.